Hello my dear students, welcome to the next lecture of digital signal processing. Today we will discuss about the important tool that has been used massively in digital signal processing computations. So that's the jet transform. So what is jet transform? So jet transform defined as power series like that, as you can see. This is the mathematical expression of jet transform, as you can see here. So you have to keep on mind this equation while solving jet transform. In any kind of function you want to solve, after jet transform, the function of ft, the time domain function will be in the jet domain function, and the equation could be written like that if it is fk. So z to the power minus k and k 0 to infinity. So there is a power series is the definition of jet transform. Some examples are there. If fk is equal to 1, so if you want to just make a power series on that equation, as you can see here, f jet will be for that particular point, if k equal to 0 means f0 k jet 0, that means f0 f0 or f1 jet minus 1, f2 jet minus 2, and so on. And if it is fk is equal to 1, so you can write that f0 f1 f2 fr all are 1, so 1 plus jet inverse minus 1 jet inverse minus 2 plus jet inverse minus 3. So that is the power series definition of jet transform. Now since we have seen that that is the power series of jet transform, just multiply the equation both sides by jet inverse, you can definitely find out this. That means when you multiply this term both by jet inverse, you will get this, and after that you will get that is jet inverse minus 1, jet inverse minus 2, jet inverse minus 3, and so on. If it's an infinite series, so the infinite series can be transformed by a binomial equation, that is 1 by 1 minus jet inverse minus 1. That is a power series conversion, that is popularly known as polynomial function conversion in mathematics. In algebra we particularly use this term. Okay, so after get this, just jet inverse minus 1, the main thing is that if you want to just solve this equation, you definitely get this series that will be z inverse minus 1 divided by 1 minus jet inverse minus 1. So after dividing by this jet inverse in that side to that, you will get this equation. So now let's see practical formation of jet transform. As you can see, there are some discrete values right there in the x-axis. There are some sample values, and definitely they have some positive, some that's equal to 1, that is less than 1. Alpha positive means the value of alpha, we consider it positive here. We consider the value of alpha positive. We consider the value of alpha is positive, but if the value of k, that means the power, is greater than 1, so that will be an exponential function like that. If it is equal to 1, you will get the value equal to that, because that is the value of k here, power. And if that is negative, value is k is less than 1, so that will be exponentially down. So that is the power series plot of jet transform. Now coming back to the next slide, that is the after doing the plot, we get this thing, that is the fz is equal to k is equal to 0 to infinity alpha k z minus k. So that is a normalized equation to understand this. So alpha is an equation, is a time of scaling factor, or you can say it's a type of a function. It can be any kind of scaling factor, or any kind of number, or anything else. So that can be used both, as it is alpha k z k minus 1. So you can write it like that. The summation will be there, and the alpha and the z both should be like that, minus 1 to the power k, and that is the power series that you transfer from there. After that, you just convert the power series like that, that you can get 1 by 1 minus alpha z inverse minus 1. That is quite similar to the previous conversion process that I have told you. Then just multiply by z, or the inverse z, just multiply by z in the numerator section, and the denominator section you will definitely get that whether the alpha z inverse minus 1 is less than 1. Note that the fz has a pole z equal to infinity on the z plane. Now there is a note some of these things, that if magnitude of pole is greater than 1, that means the k, the value of k, then the fk increases without bound, and if the magnitude of the pole is less than 1, then fk has a bounded variation. The contour z, that means the absolute value of z, is equal to 1. The z plane is of crucial significance. It is called unit circle. So why it is called unit circle? Let's find it out. That is the previous equation that we have to show at last, that the z transform. What is the z transform? But the fz has a pole at z equal to alpha. Pole means in the denominator section, as much as you get the root of the z value or s value or anything else, these are known as poles. There is a pole zero format that has been taught in the control systems. What are poles and zeros? So poles are like that. If it is z minus 1, or again is multiplied by z minus 2, and here you get the z minus 5. So whatever the root of the numerator section, and that is the denominator section, so it has two poles and one zero. The 0 is equal to z minus 5 is equal to 0. The value is 5, so that will be here. The 0 will be shown like that with a circle, and the pole would be shown like a cross. Okay, so if equation is like that, z minus 5 divided by z divided by z minus 1, sorry, z minus 5 divided by z minus 1 into, that is z minus 2. So taking 0 in both parts, you will definitely get the answer. That is the zeros, and that will be the poles. There are two poles and one zero. So if it is a pole zero format of plotting, as you can see here, so the pole will be determined as cross. That's 1 and 2 will be cross, and 5 will be 0. That is the pole and zero format. So here you can see that in z transform, if the magnitude of pole is greater than 1, then fk increases without bound, and if the magnitude of pole is less than 1, then the fk has a bounded variation. The contour z on the z plane is of a crucial significance. It is called the unit circle. Okay,